Now let's start with a new objective about alkenes, which is the isomers of alkenes. Do you remember that isomers represents the alkenes that have the same molecular formula but different structures? But here, according to the difference in the structure of alkenes, the isomers are classified into three groups. The first group of isomers is called the skeletal isomers. Two isomers are said to be skeletal isomers if the difference is in the carbon chain. For example, if an alkyl group replaces an internal hydrogen atom in the main chain, which is the case, for example, if we have a straight chain alkene and it's a branched isomer. The second group of isomers is called positional isomers. Two isomers are said to be positional isomers if the difference is in the position of the double covalent bond and the carbon chain. For example, if the double covalent bond is located at the functional carbon number 1, or in the second case it's located at the functional carbon number 2. And the third group is called geometrical isomers. Let's see now what do we mean by geometrical isomers. Two isomers are said to be geometrical isomers or stereoisomers if the difference between them is in the orientation or in the direction of the alkyl groups that surround the C double bond C. Let's take the following general form. Both compounds here are isomers, but the difference between them is in the direction or the orientation of the two alkyl groups R and R prime. In the first case, R and R prime are directed to the same side, while in the second case, R and R prime have opposite directions. So, the two compounds are called stereoisomers since the difference between them is in the orientation of the two alkyl groups. In the first case, when the two alkyl groups are directed to the same side, then this stereoisomer is called cis stereoisomer or Z stereoisomer. While in the second case, when the two alkyl groups have opposite direction, then this stereoisomer is called trans stereoisomer or E stereoisomer. But be careful that to have a stereoisomer, then each carbon atom of the C double bond C, which is called the functional carbon atom, must be attached to two different groups of atoms. For example, here, the first carbon atom is attached to a hydrogen atom and to an alkyl group R. And the second functional carbon atom is attached to a hydrogen atom and to an alkyl group R prime. Since each functional carbon atom is attached to two different groups, then here we have stereoisomers. But if the functional carbon atom is attached to the same group, for example here if we have two hydrogen atoms on the first functional carbon, then there is no stereoisomers in this case. Or if we have two CH3 groups on the first functional carbon atom, then there is no stereoisomers. So the two groups must be different on each functional carbon atom. Let's take the following example. Isomers of C4H8, where we have 4 carbon atoms and 8 hydrogen atoms. The first way to represent C4H8 is by writing it as a straight chain alkene. To write it as a straight chain alkene, here we have two ways. In the first way, we can attach the double covalent bond to the functional carbon number 1, and in the second case, we can attach the double covalent bond to the functional carbon number 2. So we will get 1 butene and 2 butene. Here, both examples A and B are called positional isomers. Why they are called positional isomers? Since the difference between them is just in the position of the double covalent bond. The third case, you can represent it as a branched chain alkene. by removing the terminal carbon atom here, CH3, and to attach it to an internal carbon atom. So you will get this structure, where the main carbon chain containing the double covalent bond here is made up from 3 carbon atoms, so its name is propene, and the alkyl group, methyl group CH3, is attached to carbon number 2, so it's called 2-methylpropene. So A and C or B and C are called skeletal isomers. Why they are called skeletal isomers? Since the difference between them is in the carbon chain. A is represented as a straight chain alkene, while C is represented as a branched chain alkene. The same for B and C. B is represented as a straight chain alkene, while C is represented as a branched chain alkene. For this reason, they are called skeletal isomers. Now, let's move to stereoisomers. Only 2-butene has stereoisomers, since in 1-butene, in the first example, the first functional carbon atom is attached to identical groups that are 2 hydrogen atoms. And the same in 2-methylpropene, the carbon atom here, the first functional carbon atom, is attached to 2 identical groups, 2 hydrogen atoms, and also the second functional carbon atom is attached to 2 identical groups, 2CH3. So only 2-butene can be represented using stereoisomers, since each carbon atom is attached to 2 different groups, hydrogen and CH3. So if the first group CH3 on the first functional carbon atom and the second CH3 on the second functional carbon atom, if they are directed to the same side, then this compound is called cis-2-butene. Cis, since they are directed to the same side. 2-butene, since the double covalent bond is attached to the functional carbon number 2. And here, if the 2 alkyl groups, 2 CH3 groups, are directed in opposite directions, they have different directions, opposite directions, so this example is called trans-2-butene. Trans, since they have opposite directions. 2-butene, since the double covalent bond is attached to the second carbon atom. So cis-2-butene, or you can represent it as Z2-butene, trans-2-butene, or you can write it as E2-butene. So these are the isomers of C4H8.